Okay, so let's try again. So as I said, journalists like to speak about Einstein because that sells paper, and even more so if he's wrong. So the funny story I want to tell you about this paper is that about 10 days before the scientific paper appeared in Physical Review in 1935, there was a leak in the press. I mean, in the people's press, not in scientific press. And this leak happened in the New York Times. That's why it was relevant to mention that before. And so about 10 days before this paper came out, in the New York Times, this came out. Einstein attacks quantum theory. And more specific, so again, you see this happened just a few days before. And when Einstein saw that, he was very, very upset. He flew in a rage, actually. He wrote to the New York Times, and what he wrote is really quite amusing. So a statement by Einstein, he says he did not authorize report on quantum theory. And the best part of what Einstein wrote to the New York Times is, so this was a couple of days later, I deprecate advance publication of any announcement in regard to such matters in the secular press. And if the New York Times is the secular press, then what it means is that Physical Review is a holy press. It turns out that it was almost certainly one of the co-authors, Boris Podolsky, who leaked that to the press. Einstein was very upset, as I said. Anyways, so what was it? What was it that Einstein did, according to the New York Times? Well, scientist Einstein and two colleagues, Podolsky and Rosen, find it, this is really hard to read if you don't know what it's about, find it not complete. It is quantum theory. But they believe that the whole description of the physical reality can be provided eventually. In other words, Einstein believes that quantum theory is incomplete, but that it can be completed. And indeed, if you look at, this is the actual paper, the scientific paper in the Holy Press that came out, there you see in a complete theory, there is an element corresponding to each element of reality. That's the very beginning. The abstract starts with it. This is the first sentence of that paper. And what we can only guess what he really meant or what they meant about this, but I think most people will agree that this was what they meant by realism. That realism means that everything that you can observe comes from something in reality. There is a real world. There is a real world, and whatever you can observe is a reflection of the real world. And Einstein considered that quantum theory did not have this. And I don't understand why the next slide will be what it will be. I'm sorry, I must have made something wrong. This was not meant to be here. Sorry, Harold. Maybe I just forgot to remove it from there when I put it in the wrong place and forgot to remove it. Pretend it didn't happen. Sorry. So, anyways, back to the New York Times. What was it that this new study suggested? Well, it was these two people. That's in Delft in the Netherlands. That's sort of funny. This is the lead student called Hansen. That's the boss called Hansen. So don't confuse them. So Hansen and Hansen, with about a dozen names in the middle, were the first people to realize an experiment that, according to the New York Times, nailed the coffin on Einstein, or in something Einstein believed. And you know about the science, the journal Science has breakthroughs of the year every year. When in 2015, guess what the breakthrough of the year was? Well, no, it was about CRISPR, but they have runner-ups. They have like 10 breakthroughs. One big winner was CRISPR, but one of the runner-ups was quantum awareness confirmed, which is what about this Delft paper. So there's something here about the runner-ups, about physicists in Netherlands demonstrated beyond a reasonable doubt that such remote influence exists. What remote influence? That if, in some cases, quantum theory seems to say that if you do something here, there's instantaneously an effect over there. And that's what Einstein sort of predicted and at the same time rejected. All right, and now is the right place to say that Hansen and Hansen were indeed the first to do it, but if it hadn't been for a very unfortunate accident, it would have been Harold who would have done it first. In an alternative universe. Anyways, let me be more precise about what this is. So, back again to the New York Times. Scientists, Hansen and Hansen, proved that objects separated by a great distance can instantaneously affect each other. In other words, there's what Einstein called spooky action at a distance. That you do something here, and there's an effect, instantaneous effect over there. So this is what most people think that the Einstein-Podolsky-Rosen 1935 paper says, but it's not. So that paper was about what we call loophole-free test of Bell inequalities. And I will explain a bit what it means in a moment. But first, what about Bell? This is not the inventor of the telephone. This is John Bell at the time. And John Bell, well, I added so-called because there's no such thing as a loophole-free test of Bell inequalities. But the main point of my talk is to explain what I mean by that. But what Bell proved, or what people think Bell proved, is that it's impossible for nature to be local realistic. Or more precisely, if nature follows the rules of quantum theory, we can never be sure that we have found the correct rules of, but assume that nature follows the rules and realistic. This is it's what an proof. Bell proves that it's Bell is most famous but he said that his proof was proof that he lacked imagination. Einstein a bit more, which is that imagination is more important than knowledge. And the question is, with enough imagination, can you get away, can you get around Bell's impossibility proof and again have a universe, a nature that is local and realistic? And the answer is yes. All right, so let me tell you what is the usual argument against local realism. First, quantum theory cannot be described by local hidden variables. Sorry for the jargon. I'll explain what it means in a moment. But statement one, there is a type of local realism called local hidden variables, and quantum theory cannot be described by that. Statement two, any local realistic world must be described by local hidden variable theory. And therefore, it follows that quantum theory cannot be local realistic. And if we believe that quantum theory describes nature, then nature cannot be local realistic. So statement 1 is correct. This is Bell's theorem. In 1964, Bell So let me tell you what it means to be local and what it means to be realistic. All right, a theory can be local, it can be realistic, it can also be something we call non-signaling. And I'm going to explain all three terms before we go any further. And I will do that with cartoons, so it's really nothing technical at the moment. Let's start with non-signaling. So in order to tell you what a non-signaling theory is, let me first tell you what a signaling theory would be. Non-signaling is just not signaling. So a signaling theory goes like this. Imagine you have our two favorite characters called Alice and Bob. And they are arbitrarily distanced. And Alice has a device, some magical device, and she can turn this dial from off, she can turn it to banana or rabbit. And if Alice turns the dial to banana, then immediately, and here for pedagogical reasons this was not immediate, but in the signaling theory, as soon as Alice turns to banana, immediately a book about bananas appears at Bob's. This, by the way, is a really funny book called Banana World, and the small characters is quantum theory for primates, I think, or something like that. Whatever. And wrote this book, which is a really good introduction to quantum theory, popular science book on quantum theory. Like humans from the stem, or like primates from the other end. And read the book. Now, so if Alice turned the dial to banana, then the point is that immediately this book appears on Bob's. Whereas if she turned the book, the dial to rabbit, then immediately a book about rabbits appears at Bob. This is Schrodinger's Rabbits and another popular science book. Now the point is that Bob can tell. Bob sees one book or the other. Therefore, instantaneously, Bob knows how Alice turned the dial. That's what we call signaling. If it's it goes faster than the speed of light. It's instantaneous. As soon as Alice turned the dial, something appears at Bob's that Bob can distinguish, can notice. So Bob says, "Oh, I see. Alice turned the dial to rabbit." That's what signaling is. Non-signaling, I told you, is not signaling, but it's a bit more subtle. Because let me give you one example of a non-signaling theory. When Alice turns the dial to see banana again, then instantaneously a ghost appears at Bob. But Bob cannot see ghosts. And if instead Alice had turned to rabbit, then the same ghost would appear but turn 45 degrees. And Bob still cannot see ghosts. So from Bob's perspective, whether Alice turned the wheel or not, or if she turned it in which place, in which setting she chose, Bob cannot tell. Bob cannot see the ghost. Bob cannot see if the ghost is straight up or diagonal. Anything to Bob. All right. Bob doesn't know. This might seem a bit spooky, but in fact, that's exactly what quantum theory is about. In the case of quantum, now I'm not going to explain for those who don't know, but if you're familiar with quantum theory, think of these ghosts as either rectilinear or diagonally polarized photons. If Alice does one thing, then a photon at Bob becomes polarized either horizontally or vertically with equal probability. And it's Alice's choice that it will be one of these two. If Alice does the other thing, then the same photon becomes polarized instantaneously, either plus or minus 45 degrees. So Alice can choose which of these two things appear at Bob. But quantum theory does not allow us to distinguish a randomly polarized photon which is either horizontal or vertical from a randomly polarized diagonal photon. And therefore, even though Alice could make something appear at Bob's, this is something Bob cannot measure, cannot detect. So this is a theory that is non-signaling, even though something appeared at Bob's. Whereas the local theory goes a bit further. In the local theory, when Alice turns the dial to banana, nothing happens at Bob's. And if she turns to rabbit, the same nothing happens at Bob's. So the difference between local and non-signaling is that in the local theory, no matter what Alice does, there's no effect whatsoever at Bob's instantaneously. Whereas in non-signaling, there can be an effect as long as this effect is not detectable by any technology. It's not. This must be in principle impossible to detect. All right. This is about local and non-signaling. How about realistic? To explain what realistic means, let me introduce some old philosophy that goes to Plato, actually, or Kant. And the idea is that there is a real world. We're going to call it the nominal world. And the nominal world is the objectively real physical world. It's all that there is. So the nominal world, and in a realistic theory, there is this nominal world. It's around us. It contains everything that's really there. And then there's the phenomenal world, which is the world of perceptions. The phenomenal world is the world that gives all that can be apprehended about the physical world, about the nominal world, with the help of unlimited technology, or maybe limited by quantum theory or physics. And then there is a link between the two, which is that the nominal world will define the phenomenal world, but not vice versa. With, mathematically speaking, a function, it's an apomorphism because it preserves all kinds of properties. And so what this means is that whatever you can perceive is determined, is defined by reality, which is the nominal world. So we can think of the phenomenal world as the realm of the experimental physicist, like Harold here. Whereas the nominal world is the realm of philosophers. Because after all, we only have access, we as humans, we only have access to the phenomenal world. And if we want to think about the real world, the nominal world, it's more philosophy than science. Not that philosophy is not a science, but it might seem like, why would a physicist be interested in something that cannot be apprehended? Because by definition, we have no access to the nominal world. We only have access to the phenomenal world. But in fact, we do have access to the nominal world, but we have access by pure thought. We have access to the nominal world by interpreting what we actually can see. So it's an indirect access. We can also think of the phenomenal world as being the world of perceptions. That's what I said before. But instead, we can think of it as the world of illusions. So the phenomenal world is all you can actually perceive, but it's also the illusions, because that's not reality. Reality is in the nominal world. And I had given this talk for years. When someone asked me, is it a coincidence that your nominal world is red and the phenomenal world is blue? I said, what do you mean? Maybe you guessed it. So here, of course, I'm referring to the matrix. This is Morpheus. Morpheus is about to offer Neo either the red pill or the blue pill. You don't need to know the story of the matrix. If you do, it's going to be more fun, but it's irrelevant for what will follow in my talk. And then Morpheus tell Neo, it's your last chance. If you take the blue pill, end of story, you wake up and you believe whatever you want to believe. For instance, you can believe that the world is non-local. If you take the red pill, then you wake up to reality, and it's going to be painful. Reality is painful, I must warn you. This is your last chance to leave the room. Because I'm going to wake you up to reality, and there's no turning back. Okay. So, seriously. If we look at now, if you think of the state of the world, again, the nominal world is all that there is. Phenomenal is what can be apprehended, and one goes to the other. Let's now think of just a system. By a system, I don't want to be precise. A system can be a particle, a human, a planet. It doesn't matter. Any system has a nominal state and a phenomenal state with the same definitions. And now it becomes interesting if we think of evolution. A system can evolve. A person can move. A particle can be measured. And so there is the nominal state of a system at time t0. And after some evolution, you get its state at time t1. So the state of the real state of the system evolves. And this gives rise to an evolution at the nominal level, but it's a shadow. In reality takes place here, but there's a shadow at the phenomenal level, which we can actually observe. And this induces a transformation at the phenomenal level, which we will call U with the same symbol. Although we can only manipulate the nominal level, it induces this transformation at the level of things that we can actually apprehend. And we see that this diagram commutes in mathematics. It means that if you go this way or that way, you get the same result. That's why it's called an epimorphism, actually. Very well. Now let's look at, for simplicity, a given system A. A could be, again, a particle, a person, or whatever. So the nominal state will be denoted by n for nominal, of system A at time 0 and time 1. And at the phenomenal level, if there are physicists in the room who haven't seen this talk before, what letter should we use to denote the phenomenal level? Any suggestion? Yep. No. Psi is thought to be reality. Psi is not, but it's not, and some people will bark. But psi is thought to be reality, so psi would be nominal. No. What is it that we can observe as experimentalists? No. I think I heard it. Anyways, the answer is a density matrix, and the letter used by physicists is rho. So rho 0 and rho 1 will denote the phenomenal states of system A. Now, the idea here, if we want to have a real world at a nominal level, and if we want it to be not only it's realistic by definition, but we also want it to be local. If we want the real world to be local, what it means is that if you have a joint state of two systems, like you have two particles next to each other, or two people, they have a state together, a joint state and AB. And it must be that this state that these two particles or these two objects can be separated physically. So you get the nominal state of A and the nominal state of B. These are projections, mathematically speaking. We use projections instead of tracing out because it's more general, mathematically speaking. But then it must be also the case that once you've split the two objects, you can put them back together and get back the original. This is what quantum theory does not allow. Standard quantum theory. Because for standard quantum theory, the state of an object, if you think of the state as being psi, as you said, then if this is entangled, it cannot be split in two psis by definition of entangled. If you think of the state as being a rho, then yes, it can be split, but it cannot be put back together. So we want this to happen. Again, it's not possible at a phenomenal level in quantum theory. And here we invent a new symbol, which we call the joint product, which is a mathematical instrument that will allow us to do that. Now, we can think of these three things at the phenomenal level using this operator. And so this is the phenomenal state of A and B together, phenomenal state of A and phenomenal state of B. So you can take the phenomenal state of AB, of the system, and you can split it in the phenomenal state of each part. And this is totally going from here to here and here to here is perfectly standard quantum theory. Although it would be done with trace out B and trace out A instead, but this is perfectly standard. However, in quantum theory, what you cannot do is put it back together. If you're not familiar with quantum theory, just take my word for it. This is essentially the reason why. Sorry. What I just is essentially the reason why most physicists believe that quantum theory. Maybe I should not say most physicists, but many physicists think that quantum theory is non-local because you cannot split things and put it back. All right. Now let me tell you what no singling means a bit more seriously than with ghosts. No singling means that if you have the state of AB, and if you apply some transformation you evolve A and B, they are together, but you evolve them together. Then you go from one state to the evolved state. If you're familiar with quantum theory, you might wonder why I don't have a tensor product here. It's because this is more general than quantum theory. This product is in algebra that I'm not going to describe. But in case of quantum theory, it would be the tensor product. Then you can project to just the state of A. So initially, the system AB is in some phenomenal state, rho AB. And using the projection, you know what is the phenomenal state of just A. So there's AB, it's some phenomenal state. You know what is the state of A. You have the state of A, and you could do something to the system, and then instead of projecting now, you could do something and then project and get the state of the system after this phenomenal state of system A after the operation. And what it means to be no signaling is that this is the same thing exactly as if you had just done a U to A. In words, you have the state of AB, which induces the state of A. If you do something to AB, whatever you do to B, V in this case, whatever you do to B, if you do U to A, let me try again. The state of A will be the same after you do U to A. The state of A will be the same after you do U to A, regardless of what you do to B. In other words, you have the system AB. Think of it as being split. You have the system AB. What this says is that no matter what you do to B, V in this case, what will happen to A is independent of what you do to B. At the phenomenal level. In other words, the person who holds system A, no matter what she does, cannot tell what Bob did on system B. Again, this is the notion of non-signaling. And notice that I did not use probabilities. Non-signaling is usually introduced in physics in terms of probabilities. We don't need probabilities to define non-signaling. Okay. Now, if I replace this diagram by its equivalent nominal version, I'm going to replace all these phenomenal states by the nominal states. This is local realism. Well, realism because it's nominal, but this is the right definition of locality. Locality means that if no matter what link there might be between A and B, no matter what I do to B, has no effect on the state of A. Not only no observable effect, which is non-signaling, but no effect at all on the state of A. So that's what locality is. All right, let's go back to the signaling. Sorry. I was going the wrong direction. Sorry about that. We have to go through this again. Sorry. All right. So let's go to principles now. Here are the principles that we're after. One principle is realism. I said it already, but I say it again. Principle of realism means that there is a real world whose state determines the outcome of all observations. That's realism. Locality means that no action taken at some point can have an instantaneous effect at some remote point. And local realism is locality plus realism, plus you need some more, because realism here did not forbid the result of an observation here from depending on the state of the world there. It only said that any observation, the result of an observation depends on the state of the world. So it could have been that when you measure here, it depends on what's there. In local realism, you will forbid that. In local realism, in addition to locality and realism, the result of an observation at some point depends only on the state of the universe at that point. And again, non-signaling is very much like locality, but we add the word observable. No action at a given point can have any observable effect on some other point. Whereas in the case of realism, there's no effect whatsoever, no signaling, no observable effect. There are two theorems. One theorem is that all local realistic theories are non-signaling. This, if you think about it, is fairly obvious intuitively. What this says is that if, no matter what Bob does here, it has no effect on Alice's state here, well, then it has no observable effect. That's what it says, no effect, and therefore no observable effect. Sorry, this was a theorem. So all local realistic theories are non-signaling. I'm going to give you a proof of that. This is going to be the only mathematics in this talk. It's just to show you that the proof is both very simple and a bit complicated because you actually need a proof. So the proof of this theorem is here. And so this uses all kinds of symbols I did not introduce and will not introduce, but I just want to show you that it's fairly, in fact, mathematically simple, just a few lines. If you're not scared of mathematics, it's easy. But this really is, in red, you have the statement of local realism, which means here, if you read that, what it means is that if on the nominal state of AB, Alice does U and Bob does V. And if you look at what's at Alice's and you look at the nominal version of it, so what can be observed? This means what can be observed by Alice after she did U and Bob did V? It's the same as what can be observed by Alice if she does U and there's no Bob anymore. So this statement really is exactly the commuting diagram that I had for local realism. Whereas the blue, this equals that, is a statement of no signaling. The blue thing is the same as the red thing, but at a phenomenal level. And here's just a proof, and a few-line proof, that indeed, if you're local realistic, then you are non-signaling. I don't want to go through this proof in any detail, I just want to flash it to you. The point of this talk is that vice versa. That all non-signaling theories are local realistic. Now, you might ask, how can that be? After all, quantum theory, at least standard quantum theory, standard meaning the Copenhagen version of Niels Bohr, standard quantum theory is non-signaling. We all agree to that. I mean, but it appears to be not local realistic, because the standard quantum theory, it appears that when you do something here, it has an effect there. Not only in a non-observable, but there is an effect. So it seems that standard quantum theory is not local realistic. So how could it be that, but it is non-signaling, so how could it be that all non-signaling theories are local realistic? There seems to be a contradiction. And my answer is this graph planar? Well, what graph? This graph. Is this graph planar? There seems to be no connection, but there is. Let me remind you, a graph is called planar if it can be, a graph is just a bunch of nodes, and you see 4 nodes and what we call edges that link the nodes. And a graph is said to be planar if it can be drawn in the plane without having 2 edges that cross. This doesn't look planar, these 2 edges are crossing. But this graph can be redrawn like this, same graph. And then you see it's planar. In other words, the analogy is that it's not because a graph is drawn in a non-planar way that it's not planar. It's not because the theory is explained in a way that's not local realistic that it's not local realistic. In fact, any theory can be made non-local. To make your favorite, let's say that you have a theory of, think of Newton's theory. Newton's theory, well, not because, well, bad example. Let's say that you have your favorite theory of physics, let's say that it is local already. You have a theory of physics that's purely local. Well, then I'm going to add invisible unicorns. And, well, I show them to you, but really they are invisible unicorns. So I take your theory exactly as it is, and I add 2 invisible unicorns at both ends of the universe. And these 2 unicorns keep chatting instantaneously to each other, having no effect whatsoever on anything you can observe. But now the theory is not local anymore. I've added a useless, non-local aspect to the theory. The theory is no longer local. See, any theory can be made non-local. It's not because you can make quantum theory non-local that it is local, that it is non-local. And the claim is that any theory that can be explained in a local way deserves to be called local, even though there are other ways to describe it that would be non-local. You don't have to buy this. Okay. Now, let me be more precise again what I mean here. What I mean is that given an appropriate definition of the nominal states, what this means is that give me any theory that is non-signaling at a nominal level. What I mean by this is that give me a set of nominal states and a set of rules of how these nominal states can evolve. And these nominal states are supposed to describe everything that can be observed. So you choose your nominal, sorry, I think I got it wrong, phenomenal. Rewind. So give me your favorite phenomenal theory, by which I mean that you give me the phenomenal state of your theory, and you tell me how this phenomenal theory evolves. And this phenomenal theory is supposed to say everything about what can be observed in the world. I'm only asking you that this phenomenal theory you give me must be non-signaling, which is a notion that exists at the phenomenal level. And what the claim is that I can take your phenomenal theory and lift it at a nominal level. At the nominal level, it would be realistic by definition. And this nominal version of your phenomenal theory will, as long as your phenomenal theory is non-signaling, my nominal theory will be local. So that's what it means, that any theory that is non-signaling, meaning at the phenomenal level, has a local realistic, meaning at the nominal level, has a local realistic interpretation or model. There is, at the moment, a caveat. We need the assumption that the theory obeys reversible dynamics, but that's the case of quantum theory. Very well. Now, how does this not go against Bell's theorem? Bell's theorem is correct. It's pure mathematics. Bell's theorem, by the way, is not physics. Bell's theorem is purely a mathematical statement which can be applied to physics in the right or the wrong way. Mathematically, Bell's theorem is correct. So how can we reconcile Bell's theorem with the statement that quantum theory can be explained in a way that's local realistic? I told you this before. I told you that Bell said it's impossible for nature to be local realistic. That's not true. He did not say that he did not say that in his famous 1964 paper. Bell said that at the very last paper in his life, with a strange title of La Nouvelle Cuisine. And indeed, in La Nouvelle Cuisine, Bell made the mistake of saying that his own 1964 theorem implies that nature cannot be local realistic. In fact, in his real theorem of 1964, said that it's impossible to explain quantum theory with local hidden variables. And that's different. That's different. So this is correct, but different from that. And therefore the question is, well, first of all, the local invariable is not the only way to be locally realistic. And I realize I didn't tell you what local hidden variables mean. It doesn't really matter. But the point is that indeed you cannot explain quantum theory with local hidden variables, but it's not the only way to be local realistic. So we need another local realistic way other than local hidden variables. And just need a bit more imagination. And there are two keys towards getting there. One is that in all these tests of Bell inequalities, bit of jargon here, I'm sorry, but in all these experiments, including the one that was touted by the New York Times as, sorry, Einstein, you were wrong. What these experiments do is that they create what we call an entangled state between two locations, sufficiently distant locations, and each side makes some measurements, chosen at random, and write down and take note of the answers. So if you think of Alice and Bob somewhere else, far enough, who does his share, initially Alice and Bob are entangled, and Alice does all kinds of measurements to his her particles, and she gets answers. And she writes down the table, question, answer, question, answer, question, answer. If you look at Alice's set of questions and answers, there's nothing spectacular. It's just purely random, actually. If you look at Bob's set of question and answer, nothing spectacular either. It's also purely random. Something strange happens only if you bring them together. It's only when you bring together Alice's observation and Bob's observation that you see emerge something that seems to be incomprehensible in a local universe, at least. And then you're tempted to say the explanation is that the universe is non-local. Because these correlations could easily be explained if there were instantaneous communications between Alice and Bob, which Einstein forbids, or I would say relativity forbids. But my point is that nothing special occurs at either side when they do their experiment. It's only when the data is brought together that something emerges. But the data cannot be brought together faster than the speed of light. And that's the whole point. So there's no need for nonlocality. You need something that goes no faster than light to see emerge these correlations. All right. This cannot be faster than light. Now you might say, what am I talking about? Alice recorded her answers, and Bob did so. It's not going to change because they bring them together. So that's why we need a second key. Because indeed, if Alice's answers were definite and Bob's as well, then yes, they will only see these correlations when they're brought together, but they were there already. So something instantaneous had happened there. So in order to make sense of number one, you need number two, which is that measurement outcomes are never fixed and definite. When you do a measurement, you think you've seen an answer, but you haven't. Or, say it better, if we think of binary measurements, you see both answers. You're not aware of it, but you actually see both answers. And so all possible results occur simultaneously. Very well. If you're familiar with the many worlds interpretation of Everett, you might say that this seems to be very much what I'm talking about. It is, to some extent. I know that Lev will disagree, but with what I'm about to say now. But however, there's a third theorem. Again, all these theorems are by Paul Raymond Robichaud, who was my student at the time. The third theorem is that in a local realistic interpretation of quantum theory, it's not possible for the nominal state of the universe to be its wave function, its quantum mechanical wave function. If you assume that the quantum mechanical wave function is the nominal state of the universe, then you cannot derive a local realistic theory in the way I described. You might argue of what local means or what realistic means, but local realistic in the way I described cannot be obtained from the assumption that a quantum mechanical wave function of the universe is the nominal state. Said otherwise, you need to add more. The wave function psi, as was suggested before, the wave function cannot be the whole description of a quantum system. If you restrict the nominal state of a quantum system, be it the universe or just one particle, if you restrict it to be its usual wave function, then this splitting and rejoining cannot be done. It's a theorem. Now, Everett's point was to solve the so-called measurement problem. He did that beautifully. He didn't want to, the point was not to resolve the locality issue, but I would say, and I think that here Lev will agree, that a hardcore Everettian, the first principle of a hardcore Everettian is precisely that the state of the universe is given by its wave function. He agrees. And what I'm saying, or what Paul is saying, is that by theorem, if you believe that, then you cannot have a local realistic universe. And here Lev does not agree. Fine, that's okay. We agree on what we agree and we don't agree. That's okay. Now, in the 1935 Einstein-Podolsky-Rosen paper, that was the title. This is the title of the paper. Can quantum mechanical description of physical reality be considered complete? And the answer is no, under the assumption of locality. If you believe in locality, then the Copenhagen Bohr's version of quantum theory cannot be considered complete if you believe in locality. And sorry about that. And what Bell, in 1987, Bell said this. That's not a 64 paper, but in 87, Bell said, either the wave function as given by the Schrödinger equation is not everything, or it is not right. And here, Bell was right. The wave function is not everything. All right. This is just to show you that the whole theory can be explained in one page. But you better go read the real paper. The fact that quantum theory can be given a local realistic explanation, in fact, was not the work of Paul. It was discovered at the end of last century by Deutsch and Hayden. Already had a completely local realistic explanation for quantum theory. So there's nothing new here. What Paul added was to generalize that to any non-signaling theory at a phenomenal level that can be explained local realistically. And in particular, the so-called non-local boxes are local realistic, or can be explained local realistically. Hence, non-local boxes are in fact local. And I will take just a few more minutes to tell you about these non-local boxes. And this is a paper that I published with Paul in Entropy, and Lev was the editor of that special issue. And he praised that paper very much in his preface, because he did. Sorry. I want to stress that this was entirely the work of my student. This is written in the paper. Or rather, it's written in the archive version, not in the entropy version, unfortunately. And the fact that you can have non-local boxes that are local is the simplest proof that a violation of Bell inequality does not rule out local realism. The point of that paper is to be extremely simple, no physics, not much mathematics. And in that paper, what is shown is that one can dream up a fantasy world, and which is not at all meant to be our reality, but it's a fantasy world whose interest is that it's local and realistic, yet it violates Bell's inequalities even more than quantum theory. And therefore, it's not because you can violate Bell's inequalities in our world that our world is not local realistic. That's the point of it. So again, all these so-called loophole-free experiments of Bell inequalities are no proof that the world is non-local. They're only adding more and more credence to quantum theory being correct. But quantum theory can be local realistic. And therefore, no matter what experiment you do to violate Bell's inequalities, you add nothing to the belief that the world is non-local. From my perspective, since I believe in locality, all you do is you add credence to many worlds, because you could not explain it otherwise. All right, so the non-local boxes being local can be explained also in a single page, but instead of mathematics, it's just a bunch of little drawings. So let me just give Give me a few minutes to go through this, and then we'll be done. So here's the imaginary world. In the imaginary world, these slides were made by two students of Stefan Wolf from drawings by someone that Paul knew. All right. And there were similar ideas, and the Schrodinger's rabbit book that I showed at the beginning has some similar ideas way before us. All right, so Alice and Bob. In the imaginary world, Alice and Bob, they have spaceships, and they have non-local boxes. So think of Alice and Bob, they each hold a box in their hand, and these boxes have the following properties. First of all, this was invented theoretically by Popescu and Holish in 1994, a while ago. So when Alice pushes, Alice's box, each box has two buttons, 0 and 1, and if Alice pushes, say, the button 1 on her box, then her box it seems that her box will either flash green or red with equal probability. And once the button is pushed, the box flashes a color and will forever flash that color. It's a one-time use. So Alice has that box, and Bob has one too. And this box follow the following magic rule. The magic rule is that if Alice and Bob both push the 0 button, then they either both see red or both see green. Same thing if one pushes 0, the other pushes 1. But if they both push 1, then they see different colors. If one sees red, the other one sees green. So that's the magic rule. The magic rule is that you see a random color, but the other box, the other guy will see either the same color or not, see a different color if and only if they both push the 1 button. And it turns out, so to summarize, they come in pairs, push the button, you see a color, and the magic rule is this. Now, Alice and Bob go and they experiment with their boxes. They are arbitrarily far away. Alice flips a coin. She gets 1, so she pushes the 1 button. She pushes the 1 button, and she sees green. Now, what can Alice say? Alice has pushed 1, and she's seen green. If you remember the magic rule, it means she knows this. She knows that if Bob pushes 0, then there will be a 0 and a 1 pushed, therefore they should be the same color. The magic rule, I remind you, is that if they both push 1, they see different colors. So Alice knows that if Bob pushes 0, he will see the same color, green, but if he pushes 1, then he will see the different color, red. Alice knows this because she pushed button 1, she saw a color, and therefore she knows exactly what Bob will see for each button he can push. So it seems for Alice that Bob's box is deterministic. And that was the whole EPO argument in 1935. The behavior of Bob's box seems to be predetermined. And this is true for whichever button Alice has pushed. And the same way, if Bob pushes a button, the same reasoning will say that Alice's box had to be predetermined. So they do an experiment, and they do that several times, and several times, and several times. And the box, it works all the time. All the time they get this magic rule. So these are perfect boxes. Now, in the real world, they can't exist. In the real world, this is imaginary. In the real world, we cannot do that. So we need to talk about imperfect non-local boxes. The imperfect box follows the magic rule with some probability p, and the opposite rule, probability 1 minus p. And according to classical physics, you cannot get a better than 75% non-local box. It's fairly easy to program non-local boxes classically, and they will work 3 times out of 4. But quantum theory can get it 85% of the time. And that's the usual argument that quantum theory is non-local. Because classically, you could get 100% classically if you allow the 2 boxes to communicate. It's only if they have to be local that you cannot do better than 3/4. And quantum theory gets 85%, and therefore, quantum theory is non-local. That's the usual argument. Not so fast. Now I'm going to show you, so the usual conclusion is that any world that has non-local boxes that work better than 75% cannot be both required and realistic, in particular quantum world. All right. And now let me show you how to get perfect non-local boxes in a local realistic world. And that will give you an idea of how you can do quantum theory in the same way, although quantum theory is a lot harder to do. And this is a theory that Paul called parallel lives. Alice and Bob are in their spaceships, arbitrarily far apart. There they are. Let's look at Alice. Let's say Alice pushes the button 0, 1. Alice pushes 1. Alice pushes 1, and she sees something. Well, no. What happened is not that she sees one or the other. She thinks that. But in fact, when Alice pushes 1, she splits. She splits in two. One Alice sees red, the other Alice sees green. The two Alices have no idea that there's another Alice. They are totally unaware of the existence of the other. So there's a green Alice, there's a red Alice, they're in the same spot in space, but in sort of parallel universes. Now, so I said, neither is aware from the other. In this split, this is why it's called parallel lives. It's a local splitting. When Alice pushes a button, she splits with her box in her spaceship, and this split will ripple through space, but no faster than the speed of light. So there will be no need for faster than light communication whatsoever to get non-local boxes locally. In particular, there's no effect on Bob, not instantaneously at least. There's a split at Alice's, but Bob is totally unaffected. Now, what if Bob pushes? What if Bob now pushes, let's say, button 0? Alice had pushed 1, and now what if Bob pushes 0? Then you guessed it, I suppose. Bob splits. There's one red Bob, one green Bob. You have two Alices, two Bobs. In a sense, 4 universes, but it's really a local split. 2 Alices here, 2 Bobs here. The rest of the universe has not split at all. And now, what happens, and they're totally independent, now becomes the magic. If Alice and Bob now decide to meet, because they want to check if the boxes work properly. Careful, 1, 2, 3, ignition. All right, so now they're going to meet, and when they meet, because Alice had pushed 1 and Bob had pushed 0, the green Alice will see the red Bob, the green Alice will see the green Bob, and the red Alice will see the red Bob. Because they didn't both push 1, each Alice will see the Bob who saw the same color. There were 2 Alices, 2 Bobs, and if Alice, let's say if the green Alice goes towards the red Bob, in this case, they will just go through each other without noticing each other. In this case, the green Alice can only see the green Bob. But it could have been that they both push 1. If they both push 1, then the green Alice will only see the red Bob, because if they both push 1, they should see different colors. So that's what I meant by it's only when you bring the data together that a correlation occurs. So you needed both keys. There's no magic correlation instantaneously, because there's 2 Alice, 2 Bob. But when they meet, when the data meets, then the correlation is made. Only then. And nothing happens faster than light. All right, so that's the idea. You can have all combinations, Alice and Bob, of course. So the conclusion, the key idea here is that in our imaginary world, the EPR argument does not hold because whenever Alice pushes a button, she can predict something about Bob. That's not what happens. Really what happens is that she predicts not what's happening at Bob's instantaneously, because nothing happens at Bob's when Alice does something. What she can predict is not something that happens at Bob's. What she predicts is how their future lives will interact. But the future life will not happen faster than the speed of light. All right, so this proves that it's wrong to claim that any world that violates Bell's inequalities has to be non-local, because that's a very simple, imaginary, yes, but it's a very simple world in which Bell's inequalities are violated, and that world is so-called realistic. So again, any violation of Bell's inequalities in our world has no implication that our world is non-local. All right, enough. Thanks for your attention.
Thank you very much, Lev, for this nice talk. I'm wondering how many students I have now.
How many students what?
I had, with all the many experiments and measurements they made, when they always started splitting.
Oh, no. As I said, all these experiments are extremely useful because they prove nonlocality. Sorry. Because they prove many worlds. Okay. Which is a very useful thing to do.
No questions, real questions. Left your second.
So, in the first, I think maybe 2/3 of the talk, you was talking about this action at a distance and problems, and then said that if we'll accept Everett, we don't have action at a distance and solve this measurement problem of action at the distance of measurement problem. But then you still was not happy and decided that you need some additional, this postulate. You said Bell said so, but Bell is not Einstein. So I don't think you can rely on him. And I don't know, do you think Einstein would be happy if you'll see Everett? And why you are not happy with Everett?
Well, we know that Bohr was not happy with Everett. We know that Bohr was not happy with Everett because Bohr lived long enough to meet Everett. But what Einstein would have thought I think that the two most sad things about Einstein's premature death, he wasn't that young, but is that he did not live to see Bell's theorem, and he did not live to see Everett's interpretation. It would have been very interesting to see how he would have reacted to each one of those two. Of course, we will never know. I'd like to believe that, contrary to Bohr, he would have embarked in many worlds, because there's no other reasonable explanation. At least for someone like him who believed in local realism. But then, I just said that Everett's interpretation does not explain local realism correctly because we disagree on the definitions. So from my perspective, or from Paul's perspective, we need to add something that you don't think is necessary to make it really local. It's only because we don't agree on what local means. It's a matter of words, of what locality is not the same for you and me. With the definition of locality I gave, then it's a theorem that a wave function of the universe cannot be the nominal state. With your definition of locality, it can. So what can I say?
Will you agree that our difference is that I admit that the world is non-local in the sense that there is no action, in the sense that it's not separable, but it is local because there is no action at a distance. So if we'll spell out non-locality in two concepts, one is action at a distance and one non-separability.
Yeah.
And so you, and I might agree, there is it would be nice to have everything. But action at a distance, this is what's kind of the most problematic thing, which you explained during the 2/3 of your talk.
Yeah, sure. Now, so where we do agree is that with Everett's interpretation as it is, with a wave function being the state of the universe, it is not separable. We agree on that. Where we disagree is is if there's a difference in what should be called separable and what should be called local. And so you see three different levels, where I see two, and that's where we disagree. But we've discussed that enough times that we will not resolve it now.
Questions? More questions here?
So you were talking about Alice and Bob's, both worlds were splitting locally, and I don't quite understand how both worlds can split locally and they then still meet according to the rules. So that sounds like there should be something non-local going on if both worlds split locally, but I mean, if both worlds split locally, then there should be the possibility of the not magic rule following color to happen and to occur.
I don't think I understand what you mean. There is a, if we go back to let's say here, sorry. Which way are we to? Fast forward. All right, so at this point, Alice has split already, and now Bob splits, now to Alice to Bob. And what I'm saying is that when they meet, so at the moment, before they meet, there are these two Alices, there's these two Bobs. Each Alice is unaware of the other Alice, same for Bob. And neither Alice can see either of the Bobs because they're too far away. You cannot see them at the speed of light. They cannot see what's going on that far in distance. And now when they meet, this happens, which means that there is a green Alice, there's a green Bob. The green Alice is in a bubble, and the bubble knows that button 1 was pushed. The green Bob is in a bubble, knowing that button 0 was pushed. These two bubbles know that they are allowed to meet. Don't ask me how it's possible. It's a fantasy world. The point is that this knowledge is local. The information is local in Alice's bubble, that button 1 was pushed and green was seen. And it's locally in Bob's bottle that button 0 was pushed and green was seen. So the information is locally available for this meeting to take place. Okay? So the whole thing is purely local. It is a fantasy. There's no point trying to explain how it's possible, because it's not possible. These boxes cannot exist 100% according to quantum theory, and we believe in quantum theory. But as long as we agree it's a fantasy world, there's no problem. The whole point is that everything happens in a purely local manner. Thanks for the question.
More questions here? No, are there online some questions? No? Actually, I mean, what I understood is that this nominal state would be the solution then to it. Do you have an idea how to get there? I mean, if we only see always our psi, and this is not it. Okay.
I did not explain how to do it. That would have been a technical talk. It's meant to be
it would
But we know how to do it.
You know.
No, it's not, sorry. From what I said, you could infer that the only thing that I proved in this talk is that we cannot conclude that the world is non-local just because Bell's inequalities are violated. That as such in no way proves that we can explain it all in a local way. It only proves that you cannot dismiss it. So then you have to work harder. So what I just showed you with these spaceships was Paul's first idea. It took 2 or 3 years of work after that to get quantum theory to fit in the picture. But yes, we know how he found out. So he has a complete way to lift quantum theory from the phenomenal level at which Bohr left it. And at the phenomenal level, Bohr and Einstein would agree. And Paul found a way to lift this phenomenal world to a nominal level that is local realistic, and that gives exactly the same predictions. Okay? And that I did not explain. That's a PhD thesis.
Yasmin, just a second.
So maybe I have a bit of a technical question. So you mentioned the PR boxes and that classical local hidden variable theories get it 75% right, and quantum
I'm sorry. Please speak slower and louder.
Okay, you
slower.
mentioned the PR boxes.
Yes.
And local hidden variables get it 75% right, and quantum theory 85% right.
Yes.
Do you know what state achieves this, or what kind of state?
Oh, okay. So to build non-local boxes with quantum theory that work 85% of the time, all you need is a pair of entangled particles in a Bell state, and Alice makes one of two possible measurements, depending on whether button 01 is pushed, and Bob one of two other measurements, these two for Alice, these two for Bob, whatever. And you just have to assign zeros and ones in the right way to the two answers Alice can get and two answers that Bob can get. So you will choose 1, 0, 0, 1, so that each pair of angles on Alice and Bob are fairly close at pi over 8 distance in polarization, except when the answer is 1, which would be at a distance, an angle distance of 3 pi over 8, and cosine squared pi over 8 is about 85%, and sine squared pi over 3 pi over 8 is about 85% as well. So that's how it's done. And these experiments can be done in real life, although you will never get 85% because it won't be perfect.
Good. More questions? No? Good. If this is not the case, then thanks a lot again, Gilles.